Hello, and thank you for joining this online presentation of our modular RF receive chain. You can find more details on our GitHub page. The motivation for this work is the 4.7 Tesla scanner that we have at the University of Alberta. It's a whole body magnet, and the scanner was assembled using parts from different vendors. Initially, it only had 4 receiver channels, but now it's been upgraded to 32. So we also need to upgrade the receive chain. We need this receive chain to provide second stage amplification for coils that already have onboard low noise preamps. We realized also that this was probably a frequent need in the community of people who build their own MRI scanners. So we wanted this design to be as modular as possible and customizable. For example, in terms of the number of channels that it supported, the frequency, the gain that it provides, and the supply voltages that it can work with. We wanted this system to be as future-proof as possible in case we needed to replace some components down the road. We didn't want to have to redesign the boards. And finally, if we want to minimize the cost. This is the high-level circuit diagram for one channel. It begins over here on the left with the connector for the RF coil. So we have RF coming in here, left to right. Thanks to this first bias T here, we're able to provide a DC output at this connector that can be used to power the preamp or even provide the detune bias for the pin diodes. The footprint of this connector is standard, so you can use SMA, SMB, or a variety of other RF connectors. The gain block here uses a standard SOT89 package. There are literally tens and tens of different gain blocks that that they use this package, and you can pick the device that you want based on the requirements of your application. So in terms of frequency range, gain, noise figure, etc. The second bias T here powers the amplifier. And finally, here at the end, we have the programmable attenuator that can be controlled digitally. The signal is then fed out through a connector. This is the circuit board layout for one channel. At the top here, we have the RF signal path. In the middle, we have the 2 bias Ts with a lot of redundant pads for components. You might need different pads depending on the sizes of components that you pick. That will allow you to accommodate for different frequency of operation. Especially the inductors here will change in dimensions as the frequency changes. Over here on the right, we have the digital control lines for the attenuator. They all come together in the header along with the DC power that comes in from the motherboard. The motherboard can accommodate up to 32 individual daughter boards along these 2 rows. If you need more channels, you can actually daisy chain additional motherboards. On the top here, we have connections and circuits to control the attenuators, while down here we have the power section, which includes pads for 3 separate voltage regulators. We decided to put the voltage regulators here because if you have your power supplies in the equipment room, once you try to power this many channels, you will probably suffer a voltage drop. And so it's best to do your voltage regulation here if at all possible. These are photos of the assembled system according to our configuration. And you can see the positions of the connections for the attenuators and the power section of the motherboard. With our configuration, we obtain a mean gain across the 32 boards of 15.4 dB at 200 megahertz. The noise figure is 1.8 dB nominally. Impedance is 50 ohms. The attenuator allows an attenuation of 0 to 31.5 dB in 0.5 dB steps. And for the supply rails, we've used low voltage drop regulators to provide two 5-volt rails, one for the digital side and one for the RF side. As I said earlier, redundant footprints are provided throughout the board design. I'll conclude by thanking the support of these institutions, the help from these people, and finally I want to thank you for your attention.